All right, our last video on 2-5. Wow, this is a lot of notes, isn't it? Whew. Okay, we're gonna get through all these. All right, so finally, the rate of change. We're talking about slope as rate of change. Remember we talked about at the very beginning that slope really just means the rate of change. How fast is this line or function changing? And we're talking about instantaneous rate of change when we talk about derivatives, and we're talking about average rate of change when we're talking about secant lines. So what the heck does all that mean? That's just a bunch of math mumbo jumbo, right? Okay, so average rate of change is stuff that you've been finding for so long, right? This is when you talk about the case of the missing speedometer, right? We talked about this. If I wanted to figure out how fast I was going, I could say, well, I know from Billings to Roundup, it's 45 miles, and I know that I did it in this much time. So I would take my change in miles and my change in time, and I would compare those to figure out how fast I went on average. And I would figure out, oh, I averaged about 70 miles per hour, right? So I would say, you know, the change in miles over the change in hours, and I would figure out how fast I actually went, okay? Well, that's an average rate of change, right? Because at any point in that trip, I might have been going 80 and I might have been going 30, right? You know, it's like right past, like you go right past the police officer and you're like, sweet, now I can speed up a little bit. Okay, no, we never do that. So when you do something like that, then you're going faster, right? But then you get stuck behind the hay trucks going up to Roundup and you go slower, right? So at any given moment on your trip, you're going a different speed. But to figure out how far you went or how fast you went on average, you would just find the change in y over the change in x, right? The change in one value over the change in the other value. But that's all algebra. That's stuff we've done for a long time. Now we're talking about instantaneous rate of change. So we're talking about how fast am I going at this exact second? How fast is my speedometer going at this exact second? At 1 millisecond, how fast is this particle moving in space? That is what we're using now to figure out, that's what we're using our derivatives to figure out. Okay, so you're gonna see something like average rate of change, AROC, and we know that just means the change in y over the change in x, right? y2 minus y1, x2 minus x1. It's just a slope, right? It's the slope between 2 points. An instantaneous rate of change is our derivative. And that's where we actually need our calculus. So let's find the average rate of change on this function from 10 to 30, okay? So first we're gonna find f of 10 and f of 30, right? We're saying at this point, how far away am I from this point? What's my average rate of change from this point to this point? Well, when x equals 10, we have 10 cubed plus 2 times 10. Okay, and so then we have, that equals 1,000 plus 20, so that equals 1,020, okay? So when x equals 10, y equals 1,020. When I plug 10 into my function, I get out 1,020. All right, then if I have f of 30, I plug 30 into my function and I go 30 cubed plus 2 times 30. Well, 30 cubed is 27,000 plus 60. So it's 27,060. So when x equals 30, y equals 27,060. So now I have 2 points. This is 1 point on my curve, and this is another point on my curve. And what I'm trying to do is find out the average rate of change between these 2 points. So it's just our standard slope formula. You know, this isn't a line, this is a curve, but we're figuring out, you know, if I averaged the rate of change from this point to this point all together, what would my average rate of change be? So then, this is when we just do y2 minus y1 over x2 minus x1. So I do 27,060 minus 1,020 over 30 minus 10, which gives me I had the math written down in my other book. Yeah, we're not doing that math at 6:30 at night. It gives me 1,302. So the average rate of change from this point to this point is 1,302. So if I was saying at time 10 minutes, I was this far, and at time 30 minutes, I was this far, how fast was I going on average? I was going 1,302 miles an hour, which, yeah, that's fast. But that's what we're asking, or that's what we're talking about. Okay, so now let's find instantaneous rate of change when x equals 10. So again, this is where we're trying to find what is my exact speedometer reading, what is the exact value that I'm going, how fast am I changing at this very second when x equals 10. So we're going to find the derivative, so f prime of x, so we have 3x squared plus 2 by, my power rules. Okay, so this is my derivative, and then I want to find f prime of 10, right, because that's my instantaneous rate of change. So 3 times 10 squared plus 2, so f prime of 10 equals 300 plus 2, so f prime of 10 equals 302, and so then I could say my instantaneous rate of change equals 302. So we could say, if that's the curve for my speed, which would be ridiculous because I would be accelerating really quickly. But if that was the curve for my speed, I could say at 10 minutes, I was going exactly this fast. All right? And that's the end of our examples. So I hope you loved watching all of these amazing videos, and I hope you got a little bit of help understanding this stuff. And we will practice some more in class.